Okay, so we continue with the analysis of behavioral patterns. We still have two to analyze. And then later today we will start also to look at some programming technique using templates in C++. So yesterday we have analyzed the visitor pattern, which actually is quite complicated kind of pattern. And we have seen what are the main advantages and the main disadvantages of using a visitor. And visitor is also a very flexible thing. So you can apply visitor to any complex data structure that you want to visit in a flexible way. So we have seen what is the content of the original pattern as described in the book Design Patterns by Gamma, Visides, Helm, and Johnson. And then we have seen a more modern application by using templates in C++. Then we have seen how to write an interpret, and in particular we have seen how to structure an abstract syntax tree using interpret. And we have seen command. Command is a very generic and general pattern that is used for encapsulating actions inside objects. Okay. We are going to come back to the command pattern later on when we are going to talk a little bit about functional programming in C++. Today we start with this strange pattern. This is called state. State is a pattern that is meant for implementing objects which have an interface that looks like fixed, but internally the behavior is going to change dynamically depending on a state. So the goal of this pattern is to allow an object to change its behavior when its internal state changes. So from the external point of view, it looks like the object changes its class. So it's like it's not the same object anymore. This pattern may be useful, for example, for implementing simple state machines. A state machine is something that is used for, I mean, all of you have studied a little bit of control and automatic control, so you should know what is a state machine. And so you have inputs to the machine, and depending on the inputs, the machine is going to change its internal state and to produce different outputs depending on the state and the transition. So we want to do something similar. The object is going to behave differently depending on the state in which it is. And as you send messages to the object will change its internal state and of course also its internal behavior. So internally you implement every state with a different class and every event with a different method. Okay? Let's consider, for example, a library that implements the TCP protocol. So you are going to provide an object TCP connection, and initially the connection is empty because you have not connected yet. So initially in general the TCP connection can be in one of several different states. Initially it's void, then when the other partner of the communication responds, the communication is established, and then when you are going to close, the communication is closing, and you cannot close immediately because you have to wait for the acknowledgement by the other part, and so on. So when you are trying to do open on an object of kind TCP connection, the response and the behavior of this function open depends on the current state of the connection. Only if the connection is not yet established we can open it. And the same for close, right? So one way to implement this, the simplest way, is that you go you encode the state inside the object as a variable, and then you start coding a lot of if, then, else, and switch cases inside the function. So, for example, in the function open, you're going to check the internal variable, and then if the state is not being established, then you open. But if the state is established or something else, then you return an error. Okay? So that's the simplest way of implementing this pattern. And probably for a very simple state machine, that's the most direct and simple to do. Another way of doing that instead is to have one different class for every different state of the connection. So you are going to have one abstract class, TCP state, that implements a method for each possible request. So TCP state will have, for example, a method open. Then we'll have a method send, a method receive, and a method close. From TCP state, you are going to derive different classes, one for each possible state of the connection. So there will be a state established, there will be a state closing, there will be a state opening, and so on. And of course, the implementation of the different methods, open, read, close, is going to be different in the different derived classes. So here is the UML diagram. You have one single class, TCP connection, that acts as an interface to the client. So the client only sees the TCP connection object. So for him, it's like one single class. Doesn't see anything else. Internally, however, the implementation is that you have one pointer, state, to a class, an abstract class, TCP state. And then from this abstract class, you are going to derive several classes, one for each state in which the connection can be. Okay? So, this pattern can be applied in one of the following cases. When an object behavior depends on its state, that will change at runtime. And when operations have large, multi-part conditional statements that depend on the object state. And this state is usually represented by one or more enumerated constants. So basically, when you have different behaviors, but the interface is always the same. Okay? So you have one single interface, but different behaviors you want to establish. Then the client only sees one single class, so very simple to use, just 3 functions. Internally, then you have a pointer to the real implementation, which can be actually very complex. And this real implementation is implemented as a hierarchy of polymorphic classes. Okay? Okay, so this is the generic diagram, not just for TCP connection, for everything. So you have a context, request, and then the state, handle, and then you are going to, this context is going to point here, here, or there. It's important to say that these objects are created, and so TCP connection is going to change which object is going to point depending on the state. So, for example, at the beginning, you have a TCP state which is not established. Okay, it's closed. And then when you open, the open is going to open a connection, and as a result, is going to return a TCP established object. And so the TCP connection now should point to TCP established. Okay, so it's the dynamic behavior can be implemented by changing this pointer to point to one of the objects of the derived classes. So the participants in this pattern are context, in this case the TCP connection, which is a very simple object which just defines the interface of interest to the clients. It maintains internally a pointer to an instance of a concrete state subclass that defines the current state through a pointer to the abstract state class. Okay, and then of course this can change. Then state defines an interface for encapsulating the behavior associated to a particular state of the context. And of course, you have the concrete state subclasses, which implement the different behaviors that need to be provided by the context. So the consequences of this pattern are that it localizes state-specific behavior and partitions behavior for different states. So all behavior associated with a particular state is concentrated into a single class, concrete state. New states and transitions can be easily added. You avoid the use of large if-then-else conditional instruction, so good. However, that's not always the best, because if you have a lot of information that must be global, taking this global information and distributing and copying across state classes may not be appropriate for complex behavior, because it increases the amount of interaction and dependency between classes. So in some cases, that's not the best thing to do. Also, it makes state transition explicit, because a transition is a change in the state object, therefore it's quite visible internally. Externally, you don't see anything. So to see an example of this state pattern, you're going to see one library which I did recently, which is called TIPA. It stands for Tiny Parser. So TIPA is here. It's written entirely in C++, and it uses a lot this technique of the state pattern. So let's see how this technique is used. So yesterday I explained to you a little bit how does it work a parser. So when you want to parse something, the first thing to do is to write a sort of language. In a sort of language, what is the structure of the parser? So what is the structure of the language? Okay? So one way to do that is to write rules. For example, yesterday in the interpret pattern, we have seen these examples, or this example of rules. Okay, so in which an expression was either a literal or alternation, a sequence, a repetition, blah 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 blah. Then alternation was an expression followed by this symbol, was followed by this other symbol, and so on and so forth. So this is the grammar rules, and then from there. You need to prepare an abstract syntax tree, and the rule is quite nice. It's quite simple. Basically, for every rule, you prepare a class, more or less. Okay. And then at some point, I said, okay, there is no parser here. Parser is not part of this pattern, and so let's see how to write a parser. So how to make sure that we can read a text and transform it into an abstract syntax tree. We can do this with this parser. So in this parser, the most important concept is the concept of rule. And so we look at this rule class. So rule class uses two techniques we've already seen. The first one is called PIMP, pointer to implementation. So I have a pointer to the real implementation. So this class does not expose any implementation. It's just a very simple class which contains a pointer to an implementation rule. In this header file, the implementation rule is not stated, and actually there is a forward declaration which is not in this file. So the client of this library doesn't see anything about the implementation. He only knows there is some implementation somewhere, this implementation rule, but doesn't know anything about it. Okay? Then this class defines the interface for the rule, for usage. So for example, we have a simple constructor for an empty rule, a copy constructor when we want to copy a rule to another one. Then we have a few very simple rules. For example, a rule that matches a simple character. Okay. This is a rule that matches a simple string. This is a rule that matches a specific token. For example, I want to read an integer number. Then I have to specify what is called a token. It's not very important what is this, because otherwise we go too far into the analysis of this program. But anyway, with this class token, I can specify that I want to read an integer, or I want to read some other complex sequence of characters. Then I have the assignment between rules. I can assign one rule to another rule. I can parse a rule. I give it a parser context. We will see just very soon what is this. And that will tell me if the string matches with the language defined by this rule. Then I can do something when this rule has been processed. And I can specify a function that is going to be called when this rule has been matched. And finally, I have a few functions that are used only for internal use. They must be public, but they should not be used by the final user. Also part of the interface are these global functions. So this is a composition of two rules for obtaining a sequence of rules. And it uses backtrack in the sense that if a rule doesn't match, we go back and check again the previous rule. This instead is a sequence of rules with backtrack, with no backtrack. So if the second rule fails, the whole thing fails. This is an alternational rule. That means rule A should be matched or rule B. Then I have a repetition of rules. And this instead is the, let's say, optional rule. We can have rule A or not. We don't really. Okay? So the only thing that the user knows about this is the rule class. And then a few functions for operating on this. And that's it. Doesn't know anything else. But how this rule is implemented? Well, we have to go and open the C++ file. So, how this rule is implemented? Let's see. So, implementation rule here. So, implementation rule is a pointer to another class, which is called abstract implementation. And then doesn't do much. You can initialize an empty implementation rule. You can initialize an implementation rule with a certain abstract implementation. Then you cannot copy implementation rules. You cannot assign implementation rule. You can parse, and this is actually the rule parser that directly calls this. You can install a certain action, and then you can execute the action. So again, here we don't have the real implementation. This is a sort of second stage inside the implementation, which goes to the real behavior. And the real behavior is in this abstract implementation. And the abstract implementation, finally, is the one that should do everything. But since we can implement a different kind of rules, for example, the rule that matches a sequence, a rule that matches an alternation, a rule that matches a repetition, and so on, we implement every single type of rule as a different class, which they all derive from abstract rule. Okay? So basically, we have a structure very similar to the state pattern.
Excuse me.
Yes.
One of the guys at home told me that he's unable to see the slides. He sees us.
Oh. Do you see the slides now?
I'm asking. Yeah, it's fine.
It's fine now? Okay. So, okay, so I was telling you that the structure is very similar to this one, only there is one more class inside it. So, in TIPA, we have rule in place of context, which has a pointer to another class here in the middle, which is called implementation, to a hierarchy of classes whose base class is abs rule. And then you have several different rules coming down from there. Okay? And why this is it's necessary? Because the user doesn't know anything about what's the implementation. It only sees the fact that you have rules. And so it's nice because you can write things like that. Let's see an example. So, for example, this is a parser for arithmetic expressions written in TIPA library. So let's see how one would write a parser. So you write, first of all, the rules you need for parsing. And here we are going to have an expression, which is the root rule. Then you are going to have two rules called the primary and terminal. And then you are going to have a different kind of operation, plus, minus, multiplication, and division. Then you are going to have integer numbers, and then finally variables already. And then what is an expression? So an expression is a sequence of terms followed by op plus or op minus. And op plus is plus followed by a term. And minus is minus followed by a term. So basically an expression is something, we will see what this term means, followed by plus and term, or minus and term. And you can have many of these. So basically you can write something like x plus 5 plus 2. And this is okay because this is the first part and this is the second part. Okay, so you have x is going to be a term, then plus 5 is going to be the first iteration of op plus, and plus 2 is going to be the second iteration of op plus. what is a terminal? A terminal is this similar but with multiplication, because multiplication and division, they have a priority over plus and minus. So basically term is a primary, okay, followed by a multiplication with another primary, or by a division with another primary, and this many times. So you can have, for example, a multiplied by 5 divided by 3. And so this one is going to be the primary, this one is going to be the first iteration of op-mult, and this one is going to be the second iteration with op-div. And finally, what is a primary? A primary is an integer, or a variable, or another expression in parentheses. So basically, this is also recursive, okay? And what is an integer? Integer is just a rule that takes an integer, and variable is just a rule that takes an identifier. Identifier is different from integer because integer only contains numbers, and identifier should start with a letter, and then it must continue with numbers or other symbols. So it's the same rule as an identifier in C or in C++. Okay? And so we are ready. So if we ignore this second part, later on, what you can do is to take a string in input and put that into an object called parser context, and then parse the expression. And exp is a rule. So as you can see, you only see rules, exp primary, term, op plus, op minus, op mult. They are all object of type rule. And then you see operational rules. The exp is just a sequence, so you put together 2 or more rules, and star is another way of composing rules, and so on. So the user doesn't see any polymorphism here. There is no virtual function anywhere. It's just object that you can compose together to obtain objects at the same time. However, the behavior is quite different, because when you do exp parse, what exactly is going to be parsed depends on how this exp has been manipulated. So the internal structure is a quite complex structure, which is realized with hierarchy of objects, with virtual functions, and so on and so forth. Okay, so I don't want to go too much into the details of this program, but just to tell you that this kind of technique is used for, to hide the complexity of the structure of the state of the functioning of your program behind one single class that acts as an interface. In this case, rule is the single class that acts as an interface, and it only has very few functions. And then the whole complex behavior is hidden into this complex hierarchy abs rule, from which you are going to derive all the different objects that realize the entire behavior. Okay? So again, one single class with a pointer to an implementation, and then the implementation can be quite complex and polymorphic. This kind of technique is quite standard for many libraries in C++. Okay, so before the break, we complete this set of slides by talking about the last pattern, which is a strategy. So in strategy, we want to define a family of algorithms, encapsulate each one, and make them interchangeable. The strategy lets the algorithms vary independently from the clients that use it. So here you want to abstract one specific procedure and implement that into different implementation. And the client doesn't know anything. It only knows about the interface. Now, which exact algorithm is going to be implemented, it's hidden behind, and it's interchangeable. That means that can be customized in a different ways. This kind of pattern sometimes is also called policy. So, in general, it's useful to delegate an algorithm to a different function instead of embedding it into your code. Because when you delegate, so you use an external function to implement your algorithm, you are more general and reusable. In the sense that if in the future you want to change the algorithm, you just call a different function. Okay? This is in general. In object-oriented programming, you can do the same by using objects instead of functions. So, like we already have seen with the command pattern, also here we are encapsulating a function within an object. For example, there are many algorithms that exist for breaking a stream of text into lines. Okay, for example, for formatting reasons. For example, there is the algorithm used by LaTeX and TeX. There is another algorithm used by Word. There is an algorithm used by I don't know what, and so on and so forth. Hardwiring this algorithm into the class that uses it, it's not desirable because, again, it goes against the single responsibility principle. So the idea is let's delegate the algorithm to another object. So we could define a hierarchy of function objects that behave like function and that they are interchangeable so that we can change very easily the algorithm, or if you want, the policy for doing something. So very now you have a compositor, and this is the one that breaks the text into lines. So you can use a very simple one, stupid, just counting the number of characters or something like that, or you can use TeX, the algorithm implemented in TeX for breaking the text into line, or you can use array because you want to, for example, insert also images in a sort of table, and so on and so forth. So you have several algorithms that are doing the same thing in different ways. Client will have a pointer to a function object called compositor, and then this can point to a simple compositor or to a TeX compositor or to an array compositor, and you can decide which one to implement at the very end, or also dynamically while the code is executing. Okay. So here is the description of the different way of composing a text into a page. So the composition maintains a reference to a compositor object. So you can change the strategy both at compile time and at runtime. Why you want to use classes instead of function? Well, in object-oriented, it's why object can carry state, while function cannot. So it's more general. Okay, so we've already seen a lot of this. For example, what's the operator parenthesis here? Basically, it's a way to use the object as it were a function. And so by using this, you can basically parameterize this with respect to a certain operation. Okay? So everything for strategy. So as a conclusion for these patterns, so these are patterns that are taken directly from the book by about design patterns by the Gang of Four. So I would say that they are a little bit old right now because they are very, very focused on object-oriented programming, And in the original book, they're actually very focused on Java-like languages. Okay. Today, things have changed a little bit because, first of all, object-oriented languages are very good, and object-oriented design is in general very, very good. But there are other ways of designing programs. For example, as we will see, one of the next lectures, there is functional programming, which is considered today a very good way of organizing the code. So in one of the next lecture, we are going to talk also about functional programming. And so object-oriented programming is
Si è piantato.
In realtà mi sa che sta ancora streamando.
Cosa facciamo? Lo lasciamo andare? Vediamo se si ripiglia.
Yes, I'm still hearing you.
Prova a parlare.
Ok. Ok, maybe now it's working.
Okay. Are you still hearing me?
Not too much.
Not too much.
Yeah.
Okay, but
A certain delay.
Okay, but anyway, we are very close to the break, so I think it's time to call for a break. Okay? Can you hear me?
Okay. Okay. Yes, yes.
Sì, sì. Invece che chi streamava le slide ci riusciva. Streamare il video non ci
Professor,
Yeah.
Professor, the final project, the final assignment should be done in group or by only one of us.
Yes, it's better, yes. I decided that you should work, I mean, you can also collaborate if you want, because the project is going to be the same for everybody. So if you collaborate, it's okay. But of course, everybody should know what is going to happen.
Okay, so it's our choice.
For example, groups of
Group of two is okay?
yes, groups of two is still okay.
Okay, thank you. Yes, group of three. Oh, that only one of them. Ask me. You are going to French. So you have any thoughts about life in French? Ask. You are going to French. I can listen to you. Come, drink a beer. I invite you a beer. That can teach me how to enjoy life. This topic works.
Kom, en good coffee. Coffee.
Mi sentite adesso?
Adesso sì.
Chiaro?
Sì, sì, adesso anche il video sembra sincronizzato. Prima si vedeva molto fuori sincrono.
Immagino, sì. Ma sì, boh, vai a capire cos'è. Ogni tanto.
Intanto parte e va.
Cose complicate. Allora, ci sono domande?
No, per adesso è abbastanza chiaro.
No.
La deadline per assignment 2 è il 10, giusto? Sabato.
Sì, sì. Vabbè, accetto anche qualche un po' di ritardo defiance.
Va bene, va bene.
Visto che insomma ci sono tante cose da fare.
Una domanda, un dubbio che mi è venuto un po' di giorni fa. Se io ridefinisco un operatore, ad esempio quello di uguale uguale,
Sì,
su una classe, ad esempio, cioè usando il polimorfismo, quindi ho ad esempio una classe e poi una classe derivata. E
sì,
io ridefinisco l'operatore su entrambe le classi, cioè sia su quella base che su quella ereditata, cioè che eredita
sì.
dalla base. Se poi io ho un puntatore a una classe base, però che sta a un oggetto di quella ereditata, cioè di quella più specifica, diciamo. Cioè io creo un
Sì.
oggetto di classe più specifica, però lo punto con un puntatore di classe base. L'operatore uguale uguale, in quel caso lì, fa riferimento a quello più specifica.
No, no, se l'operatore non è quasi, cioè raramente si fanno gli operatori virtuali, eh. Di solito non è il modo corretto di agire. E per cui per capire che cosa succede, bisogna considerare che l'operatore in fondo è una funzione. Quindi uno va a capire quale tipo gli sta passando e cerca di capire su quale funzione lo sta chiamando. Quindi ad esempio, se uno sta facendo il confronto, allora, hai detto che usi due puntatori alle classi base.
Sì, cioè voglio capire se il polimorfismo vale anche per gli operatori oppure no. Cioè, se io poi vado a ridefinire un operatore, però
Nessuno
sulla
ti
classe più...
vieta di definirlo virtuale l'operatore, però bisogna stare attenti a come viene usato, perché per usare una funzione virtuale devi comunque utilizzarla attraverso un riferimento oppure un puntatore. Se la usi attraverso l'oggetto, purtroppo non viene utilizzata come funzione virtuale, ma viene utilizzata come funzione normale, cioè viene chiamata la funzione staticamente che appartiene al tipo dell'oggetto su cui la sta chiamando.
Ah, ho capito.
Per esempio, se tu scrivi, mettiamo che P è un puntatore alla classe base e tu scrivi asterisco P uguale uguale asterisco Q. Allora, asterisco P è l'oggetto inteso come oggetto della classe padre, non è più il puntatore. Cioè quando uno scrive asterisco P si sta riferendo all'oggetto e l'oggetto però viene visto come l'oggetto come se fosse della classe padre. Non so se mi sono spiegato.
Sì, no,
Eh,
penso di aver capito.
allora, se io scrivo una cosa del genere, aspetti che faccio, apro un terminale. Vede?
Sì,
Ah, quale viene chiamata di questa cosa qui? Allora, asterisco P significa la parte dell'oggetto, lo slice dell'oggetto della classe base.
sì.
Lo stesso per asterisco Q. Per cui se io la funzione dentro la classe base l'ho definita così, ok?
Sì.
La funzione che viene chiamata è questa qui e B viene considerato come un riferimento alla classe base tipo costante. Naturalmente questo è un riferimento, dis è un puntatore, quindi se qua dentro poi per esempio chiamassi mm, devo fare ok?
Sì.
Allora tutto dovrebbe funzionare bene, perché anche se questa non è virtuale, la funzione che viene chiamata è quella virtuale, quindi se per caso siamo dentro un oggetto della classe derived, Allora, quando scrivo così, viene chiamato questa funzione operator qua, che chiama la equals, però la equals è virtuale,
Quindi quella
quindi
del
è come se scrivo this freccia equal, e quindi
sì. Ok.
ok? Virtual qua, però se scrivo virtual
Sì, sì,
qui
sì.
non è chiaro cosa succede qua, capito? In generale, questo è una cosa che adesso andremo a
Sì, ho
analizzare.
capito.
Sì, in generale, questa è una cosa che andremo a dire tra un attimo, conviene le funzioni virtuali non esporle, ma farle sempre chiamare attraverso questo meccanismo un po' questo giro. E specialmente quando si tratta di uguaglianza, di coppia, eccetera, eccetera, non è quasi mai facile direttamente accedere alla funzione virtuale per il cliente. È molto meglio avere una funzione secca e poi internamente la funzione secca chiama delle funzioni virtuali.
Ok. Va bene. Grazie.
Prego.
Sì, quelli se esiste ancora il combo, sì.
Sì, però sono proprio un caso specifico. Cioè, pensato tu, se lo sentiamo in quel momento, infatti, molte così sembra sì, facciamo un progetto,
Fai una fork di catch da intratendi solo le tue girazioni.
Il progetto uno scrive su di testa e l'altro scrive
Sì. Ovviamente non lo stesso.
no, ma niente. Quindi è una cosa a fare questo non so io scrivo mi chiedono io sono sempre funziona non funziona.
So we start. So template metaprogramming. So as I said, object-oriented programming is a technique that has a lot of time behind, and now many new things have appeared. One thing I was mentioning is functional programming, but a little bit before, I mean, actually a little bit more than 10 years ago, we had also this book by Andrei Alexandrescu, which changed a little bit the way C++ programming were written. And the idea was to use much more the techniques having to do with templates for programming in C++. Some of the techniques are quite difficult, so the book is actually quite difficult, and also some of the techniques are now a little bit old, because with the new standard, some of the things described there can be done much more easily in C++ 11. So if you want, please have a look, because there are a lot of very nice and neat ideas, but consider that now it's a little bit old. So, in fact, I would like to present to you a few of these techniques, the one that I consider a little bit more interesting, because they let you know a lot about templates and the power of templates in C++. So let's start with a little bit of summary of what is a template in C++. And then, step by step, we are going to look at some of the techniques for programming with templates in C++. Like, for example, understanding if two template parameters are one derived from the others or not, or implementing one thing or the other depending on some specific parameter that is known at compile time. So let's start again clean on trying to understand what is a template. So a template is a sort of macro. It can be seen as a way to generate code. For example, if I have this program where I have a function swap, which is a template function on parameter t, and then later on I do a swap on characters, integers, and doubles, what happens is that 3 new functions are generated by this template, one for integers, one for doubles, and one for chars. So the actual generated are listed on the right. So a template is a way to generate code. Please remember this. It's quite different, for example, from what are the generics in Java. Generics in Java do not generate any code. The code is there. It's only there is some extra glue for making it generic. Here instead, we are using the template as a way for the compiler to generate code. Now, this is the simplest way to generate code. We just substitute t with the integer, char, or double. But there are many, many different ways to generate code, and some of them are very complicated. Remember, you can also make one member function as a template, like this. Okay, actually, this, as we have seen, is not going to work. The accept in a visitor is not going to work because it has to be specific for every single class. But anyway, this is a template function. And if you don't use this, the member function is not generated. So remember, every time you do generate, and if a function is not generated, it's not compiled. So, for example, if there is an error in the function, the compiler will never compile it and will never understand there is an error. At the same here, also create member functions. If you don't use it, it's not generated and it's not compiled. Also remember the important restriction. You cannot make template virtual methods. You cannot combine templates and virtual. That templates are not generated if they are not used. Consider this example. You have a class. Class is a template class with parameter t, and then you have a pointer to t inside the class. Then you have a constructor which just takes a pointer to an element of type t, and then you have a function call fun which calls member function fun on the object, and then you can get the pointer. And then you instantiate my class with integer. Now, if you instantiate my class with integer, some of the code there doesn't work. In particular, call function is not going to work because integer is a primitive value, so it has no fun member to call. Okay? However, this code does not produce any error in the compilation. Why? Because call fun is never called. And since it's never called, not generated, and so this code contains a potential error, but it's correct because calfun is never actually invoked. Okay? So remember this. If you not generate, if you not call a function, the function is not generated. Okay, then we have many different strange things. For example, a parameter could be a template. So you could have widget manager, which is a class, a template class, which derives from a policy, another class, which is itself a template. So widget manager is deriving from public creation policy widget. And creation policy is, of course, a template policy, so it's a template class, which, so you have template inside template, basically. And this is completely valid. Yeah, that's actually a policy, based design technique is going to create new widgets using the function create, which is contained into creation policy. Okay. And for example, you can have dynamic creation, and so the widget manager is going to do dynamic creation of my class, WM. So dynamic creation we just call new. Or you can have another, for example, creation on the stack, which is going to create the object in your own memory. Okay, so you can customize the way widget manager creates objects by using this creation policy. And actually, you can entirely omit the template parameter for creation policy. So you can also write like this. So here you don't need to specify the actual name of the parameter for the template class creation policy. So from here, you can go there. Another very important feature that you need to understand the following slides is template specialization. Template specialization means that you can write a general version of a template, and then later on you can write a more specialistic. For example, here you have my class that is a template class. Later on, you can write another, again the same name, but specialized for integers. So the first version is general and uses general techniques, and then by writing like this. So when you write this is going to use the general version of the template. When you write my class int n, this is going to use the specific version you provided. This is called template specialization. When you have more than one type parameter, you can specialize on a subset. For example, suppose you have a general version which depends on t and u. You want to specialize on the first version, which when t is integer, you just write like this. You can specialize on integers. You have this specialization. So when you write double double, then this uses the general version. When you write int double, that uses the first specialization, and this uses the second specialization. Okay? So the compiler performs a sort of pattern matching. It's going to look at all possible versions to see which one matches better. So it looks for the best match. So the best match for a double-double is the general version. The best match for int double is the second version. And the best match for the third one is the third version. If you specify, for example, double int, the best match is the general version. Now you have to be careful when you do these things. You can go and become ambiguous. For example, suppose you have a general version T and U. Then you specialize on the first one, and you specialize on the second one, but you do not specialize on both. Then when you write a int, best match, and the compiler doesn't know which one to choose, so it will tell you, hey, it's ambiguous, I don't know which one to choose. I cannot do it at random, of course, so you have to tell me how to do that. Okay? Another thing to know is that partial template specialization does not apply to functions. So on functions, you cannot do partial. For example, this one, it's a function that takes a parameter of type U, an object of type T. Suppose you want to specialize on T and write like this. Well, this is illegal, because if this would be allowed, fun the same parameter list, then they differ only for the return type. And as you know, in C++, you cannot have two functions which differ only on the return. Specializing on T here is illegal. The second thing, the third line here, it's another function in which apparently you are specializing on U. But actually this is not true. You are not specializing. You are doing overloading. So fun that takes a U and fun that takes a window are two versions of function fun which take a different parameter list. So they are actually two functions. So here this is overloading, it's not specialization. Okay? So this is just a little detail, but just to tell you that spatial template specialization does not work for functions. Okay, we are very close to the core part. Now, the parameters of template can also be constant. In particular, they can be constant numbers instead of types. By constant, I mean that they are things that are known at compile time. These are not variables, are things that are resolved at compile time. For example, you can write this very silly structure, num, which is templatized with a number n of type unseen. Internally, you define an element num which is equal to n. So this is a very silly thing, and you can write num of 5x, num of 8y, and then you print num for x and y. And you can get also the size of this data structure, which is equal to 1, because the data structure does not contain any data, only contains a constant. Static, by the way. So the size of this little structure is just 1 byte. And a constant can be a parameter of a template. You can also make a calculation with n, but of course this calculation can be solved, must be solved at runtime. You have to solve completely all templates at compilation time. So here should be compilation time, not runtime, sorry. So for example, you can have things like that. You can have a var num, which contains a function p, which prints this constant n. On 0, okay, and print n is 0. So depending on var num, what you give as a template parameter, if you give something different from 0, this one is going to be used. If you give something that is 0, then this one is going to be used. And again, these are constant that should be no and compile time. Okay, and now we implement a thing just templates, and that's very nice trick, because the calculation is done entirely by the compiler. So let's look at how this works. So I'm writing a tutorial which takes an integer parameter n, and internally it will define an enumeration value which is equal to n multiplied by factorial of n minus 1 value. Then I define a special. We'll try to compute this. So we'll try to resolve this. So the compiler put 5s here, and it sees that for computing this value needs to have a factorial of 4. So it put 4 here, and it sees that to compute it, it needs factorial 3, and so on and so forth. And finally, thanks to the pattern matching technique, it obtains 1. So it goes back, and finally it computes the real value for the factorial of 5. So let's see how this works. I'm going to open the file. I think I don't have it, sorry. I have very complex things, but I have this, so let's copy and compile. Okay, so you have this structure. It's the specialization. And then we write a simple main in which we are going to print. Okay. Okay. So the result is 120. It's important to understand that this result, 120, is computed by the compiler. So there is no actual computation done at runtime here. The compiler here substitutes the actual value, so 120, computed by himself. So if you put something, of course, larger, the compiler will be to compute. So we know now how to compute the factorial of a number through the compiler. Of course, it's not very useful, right? We need something a little bit more useful, but that's already a nice technique because it basically combines two of the properties of the templates. And the first property is the template specialization. And the second property is the fact that everything is compiled on the fly, only when needed. Okay, so let's continue and let's see if we can do something a little bit more useful than a factorial. So, first of all, let's analyze what is a type in C++. So in C++, a type is a type, and you don't need much for defining a type. You just define a structure like this. So simple is a type, another simple is a different type, and yet another simple, it's another type. So you have three different types here. Okay. Of course, you cannot do much with such types except telling the compiler that a certain type exists. So you are defining this type. And also, you are not really, you don't have any runtime code associated with these types. And if you do size of simple, that returns 1. Exactly like doing the size of nu would return 1. Okay, because it's an empty type. There is no data associated with it. And the same here, simple has nothing associated with it, so its size is 1. Okay, so now look at this code. This is also very strange, but also you have a structure cont which inside has nothing but a type def. T my type. So basically you are defining T as my type. And so when you do cont int my type, you are basically obtaining an integer. And when you do cont double my type, you have a double. Okay? So again, this is very stupid. It doesn't serve anything. But just remember as no runtime associated with that. So it's not very different from simple. Okay. So this is a very basic things. Very stupid, very silly. I just show them to you to try to understand the basics. Try to apply them for doing something useful. An integer and you need a new type. So one way to do that is a template which takes an integer and associate it with a value, an enumerated value. So this template actually generates a new type for each integral number it is passed. Now we use this for doing what is called that compile time dispatch. So the technique I would like to tell you is compile time dispatch. So you want to select one of several functions to be called, and you want to do this selection at compile time, depending on a compile time constant. So runtime dispatch is something that depends on the value of certain variables. They are only known at runtime. Typically, runtime dispatch by using if then else, or by using a switch case, or by using virtual functions in dynamic banding. Something, and then either you call a virtual function, which is going to tell, or you check something, and then you execute one or the other, depending on what you have to do. So this is called, okay. Of course, you can also do runtime dispatching based on compiler. I don't know, factorial of 5 is less than 100, do this, otherwise you do that. You know how much is it a factorial of 5 statically, it's a compile time constant, so you can do dispatch based on compile time constant as well. However, this is not always possible, and let's see an example. Suppose you are designing a container, and your container is going to be a template, because you want the container to contain everything. You want to contain integers, but also very complex types, but also pointers. Okay? Now it's a type container, but copying all the contained objects. So suppose your container contains, I don't know, my class. Okay? When you want it to be copied, of course, right? Now, to duplicate the contained object, you can call it the copy constructor, of course, but this maybe is not always available. In fact, sometimes when you have a hierarchy of classes that implement polymorphic methods, very often you disable the copy constructor because the copy constructor doesn't work very well with the hierarchy of classes. In particular, if you have a pointer to an object and you dereference it and you pass to a function, then the copy is going to slice the object. And this is something you don't want. Actually, you want to be able to copy, right? So copying means that you have various ways of copying objects. In particular, we consider two cases. Polymorphic types. This means hierarchy of base class and derived classes, and you have virtual functions, and you treat these objects by using pointers. Okay, so you are going to have class base somewhere, and then you are going to have class derived. And then you are going to derive from base in this way. And then you are going to have base star p equal new derived. Okay, and at some point, okay, so that doesn't matter. So at some point you need to copy it. And so you would do something like base q equal star p. Now this is not very correct. Why? Because p is a pointer to base. And when you do this, what you obtain is an object of type base, not of type derived. And you pass this to Q, so Q is going to take one part of derived and slice it. We have already seen this in one lecture, if I remember well, when we talked about slicing objects. So when you have polymorphic types, that's not the most correct way of designing your code. One better way to design your code is to disable a copy constructor. Okay, both in the base and the derived classes. So you avoid using the copy constructor directly. And if you really want to copy the object, you use one function, virtual function, clone, which is going to basically copy the existing object and obtain a new version. Okay? So this works. Why? Because as you remember, it's legal to change the return type of a virtual function if the types are consistent with the hierarchy. So here clone will return a base, here clone will return a derived. This is legal in C++. And so now if you really want to copy, what you are going to do is something like okay? So for polymorphic types, if you want to copy, you should use this technique, the clone technique. For non-polymorphic types instead, you should use the copy constructor. So copying is different depending on if the type is polymorphic, so part of a hierarchy of classes with virtual methods, or non-polymorphic. If the type is polymorphic, you should use the clone. Of course, this is in general. There are exceptions to these rules, but the most clean technique for programming is polymorphic types are copied by using a clone function. Non-polymorphic types are copied using copy constructor. Okay? Now let's go back at our original problem. We have a class myContainer. We want to implement this myContainer, and we want to copy myContainer. Now we are in trouble, because if myContainer, which is a template class, if it contains polymorphic types, it should use clone for copying the internal object. Otherwise, it should use a copy constructor, right? So we have this problem. We want to copy. How do we copy internal objects? If it contains polymorphic types, we should use clone. Otherwise, should use copy constructor. Okay? So the choice of calling the clone or the copy constructor depends on whether the class is polymorphic or not. So basically, this depends on the compile time Boolean constant. Is polymorphic. Now, the following code, which is quite straightforward, doesn't work. Let's see what the following code does. So suppose we write class T, bool is polymorphic. Class T is the type we have inside the container. It's polymorphic. It's a compile time constant that we pass to the container, which tells if T is polymorphic or not. And then in our function, we want to copy. And then we do if is polymorphic, we do p clone. Else we do new t star p. So in the first case, we are cloning. In the second case, we are using the copy constructor. Now, unfortunately, this code does not compile. Why it does not compile? Well, very simple, because, for example, for polymorphic classes, most probably the copy constructor has been hidden and deleted. And most probably, for non-polymorphic code, there is no clone function. But the fact is that the compiler has to compile both, right? He cannot eliminate one of the two. He has to compile both. Maybe the optimizer will eliminate one of the two, depending on the fact that this polymorphic is true or false. But the compiler must compile both. And then maybe the optimizer will eliminate. Okay, so we are in trouble here, because if we use if then else, both the then branch and the else branch must be compiled. So how do we solve this? We use the technique I showed before. So the compile time dispatch. We write two functions. The first one takes this pointer to P that we want to copy and uses the clone. This function takes two parameters. The first one is the pointer, the second one is an object of type int2 type, true. Very strange object. And the second function takes a type int2 type, false. Now, these two are two different types. The first one is a type which contains nothing. It's a simple data structure. I will just show you the definition. Int2 type is a simple data structure that takes an integer, and true is basically equivalent to 1, and false is equivalent to 0. So this is like int2 type 1 and int2 type 0. And these are two different types. So here is like we are passing two different types of object. The first one is int2 type 0 and the 1, and the second one is int2 type 0. So these two functions are actually different because the prototype is different since the argument list is different. These are two different types. And finally, the function that is exposed to the client for copy will just be translated into function P into type is polymorphic, where is polymorphic is a compile time. Now, if is polymorphic is true, the first version is compiled and the second version is not compiled. If its into type is polymorphic is false, the second version is compiled and the first version is not compiled. So the compiler will compile only one of the two, not the other. And which one? The correct one. So the basic trick here is there is only one of the two private functions will be compiled, the right one. So we don't run into the problem of does it have a clone, does it have the copy constructor? Because we select which function to call depending on this fake parameter. Now, there is a little extra overhead here because we are creating an object of type into type true or false, which we pass to a function without using it. In fact, I didn't even give a name to this second parameter. So there is maybe a little bit of overhead involved, but some smart compiler could also eliminate this overhead. Since the parameter is not used, maybe is not even passed. So some smart compiler could actually optimize away the second parameter and just choose the right function to compile. Okay? So this code cannot work because the clone does not exist for non-polymorphic functions, and the copy constructor does not exist for polymorphic classes. This code works because only one of the two functions is going to be compiled, and the right one. Okay? So this technique is actually called compile time dispatch because it's very similar to having an if, but at compile time. So we are dispatching which function to call, which branch, this one or this one, to execute, depending on a compile time constant. And everything is solved at compile time. Okay? So it's a very complicated trick, if you want, because we are generating strange 1 bytes types depending on a parameter. We are using the technique of not compiling code that we don't use, and everything works. And it actually solves a real problem, because you cannot write a container class which just copies everything without using this trick. Okay, I think that we can stop here, because it's already quite late, and the, the content of the following slide is even more complicated. So for today we stop here, and if you have questions, otherwise tomorrow we will continue, and we will also discuss the final assignment. Okay?
Okay.
So bye bye, see you tomorrow then.
See you tomorrow.